Okay, so my talk. The sort of the background for this, I guess, in the philosophy of physics literature is that quantum field theory, it seems to pose a challenge for philosophers in that there's a great diversity of different approaches to the theory. That's the case with many physical theories, but it's sort of seems to be kind of an unavoidable issue when you're approaching quantum field theory. In particular, there's there seem to be very different versions of quantum field theory in different sub-communities that have been developed by different sub-communities of theoretical physics. So there's been some discussion in the philosophy of physics literature. There's debate between Dorian Fraser and David Wallace, where they distinguished in particular sort of what's called axiomatic quantum field theory, which has been developed in the mathematical physics community, and then goes by various names, but conventional quantum field theory, which is sort of what people are doing in sort of mainstream theoretical physics. And these, I'm going to kind of, one of the points of the talk is like this distinction is quite a coarse one. So there's going to be lots of stuff coming under conventional quantum field theory. There are many different approaches within that heading. But the way that they've tended to be distinguished, or the categories along which they tend to be distinguished, one of them is rigour. So the axiomatic quantum field theory is a rigorous approach to quantum field theory. These conventional approaches are sort of non-rigorous. But on the other hand, axiomatic field theory is struggling to produce, to construct the realistic, empirically successful models that are used in, such as the standard model, for instance, which is like the most successful quantum field theory, whereas the non-rigorous conventional approach is very predictably successful. So that's kind of where we're at in the philosophy of physics literature for the different varieties of quantum field theory. What I'm going to be trying to do in this talk is sort of trying to sophisticate that picture a bit by focusing in particular on not the contrast between rigorous and non-rigorous approaches, but the diversity which exists within approaches to quantum field theory which are claiming to be rigorous. So within mathematical physics sort of approaches to quantum field theory. So I'm going to be basically just pointing out that axiomatic field theory is not the only approach that is being motivated by mathematical rigour. I'm going to talk about this other program that I've been working on a bit over the past few years called causal perturbation theory, and kind of talk about how we should understand this, basically, that there are different strands, there are quite different programs within mathematical physics which are each trying to make QFT rigorous in different ways, it seems. And I'm sort of going to, I'm not really going to be doing history seriously, but the way that I've been approaching this is to go back to the origins of these approaches in the 1950s. So I'm going to tell you do a kind of not very precise historical introduction to where these programs came from. The motivation for doing that, or one motivation for doing that, is it gives us a better handle on the original motivations driving these programs, which sometimes gets a bit lost when we just look at the kind of contemporary situation in the way that philosophy of physics often just looks at the contemporary versions of these programs. And another reason for being interested in this this topic of different mathematical approach to quantum field theory, and specifically in the 1950s, is arguably this kind of period was also quite important for the development of mathematical physics more broadly as a discipline. So this is kind of also the period where the first mathematical physics journals are being developed and institutions are being developed. So I guess like a broader motivation for people who aren't particularly interested in quantum field theory specifically is that looking at this period might be, and this context might be useful for thinking more broadly about how mathematical physicists are thinking about rigor more generally, and the different ways of thinking about the project of mathematical physics. Okay, so that was sort of the motivation. The motivation part of the talk. So the bulk of the talk I'm going to be sort of presenting these two different strands of mathematical quantum field theory that I talked about, axiomatic field theory and this causal perturbation theory approach. And then I'm going to finish by reflecting on how we might understand the different approaches to making physics rigorous that are driving these different programs. So some general reflections on mathematical rigor in physics. Okay, so as I said, this is going to be sort of a sort of toy historical narrative. So we're starting in the 1930s, which was the origin of quantum field theory, or maybe slightly before, but around then. The way that people like Heisenberg and Pauli originally tried to approach relativistic quantum field theory was using a perturbative expansion in the interaction coupling. So the idea there is sort of you start off with a theory with no interactions, and then we introduce a small interaction, and we want to express our observable quantities as a series in this alpha, which is kind of describing how strong the interaction is. So that might be something like the electric charge in the case of QED. And then the sort of calculational strategy is, we'll calculate a few terms in this series and then kind of cut off the series and use that as an approximation of the behaviour of the interacting theory. But the problem that physicists immediately ran into was this problem of ultraviolet divergences. So basically the issue here is that when you try and set up a series like that in the context of quantum field theory, the coefficients of the series, so this A2, the second coefficient, the second order coefficient, contains divergent integrals. So integrals like this one, which we're supposed to be integrating over all momentum. If we go up to infinitely high momentum, we get a divergent integral. So this integral is like diverging like a logarithm of the upper limit on the momentum integral. And there were various responses to this problem, but basically the main takeaway that people had in the 1930s was this suggests that quantum field theory is just an inconsistent theory. At best, it might provide some approximations in certain limited contexts, but it's going to kind of necessarily break down at high energies. In the 1940s, so many people were trying to develop alternative theories to quantum field theory during that period. In the late 1940s, after the war, a sort of more conservative response to the problem was developed with this theory of renormalization. So essentially a sort of method was developed for assigning finite values to these coefficients despite the appearance of the ultraviolet divergences. And the sort of yeah, roughly speaking, the idea is that we can sort of absorb the infinite part of the coefficients into the so-called the bare coupling or the bare mass of our theory, and we can re-express the series expansion in terms of renormalized charges and masses, and then we'll end up with finite values being assigned to the terms in the expansion. So this was kind of one way to think about this as kind of as a tactical victory. It definitely solved the calculational problem that physicists were having in the 30s. It allowed empirical predictions to be obtained from this perturbative expansion. But it didn't really lead to an end to worries about the consistency of quantum field theory. So in the 1950s, after the dust had settled, there was sort of a period of renewed crisis about whether quantum field theory is really a consistent theory, what had actually been achieved by these renormalization methods. And this is where what I'm calling mathematical quantum field theory comes in. So there was sort of a broad movement of theorists who had the idea that, in order to bring some resolution to these worries about the foundations of quantum field theory, we need to move to a higher standard of mathematical rigour. We need to make the theory more rigorous. And that's the only way that we're going to either to show that the theory is inconsistent or show that it's consistent and that models exist. One way to think about, and so this diagram, as I'm indicating here, I'm thinking of axiomatic quantum field theory and causal perturbation theory as sort of two strands of this mathematical QFT movement, this broader movement. And one way to think about these two strands is as responding to different problems with renormalized perturbation theory. So that's kind of the angle I'm going to be presenting here. So there were various problems with renormalized quantum field theory as it stood in 1950, but there's two that I'm going to focus on here. So on the one hand, there were worries about the rigour of this renormalization procedure that I described. One way to cash that out is just, it seems like the way that renormalization was being done by people like Feynman, Schwinger and Dyson involved the manipulation of these ill-defined integrals. So you're kind of subtracting these infinite contributions in a way that looks mathematically suspect, and also like the bare charge of QED, for instance, the way that someone like Dyson's expressing it is as a series with each term in the series being infinite, which also looks kind of mathematically ill-formed. And partially as a result of those sort of worries about the rigour of the renormalization procedure, there was also a lot of confusion and debate about the sort of interpretive significance of renormalization, like whether renormalization had somehow solved the problem with quantum field theory's high energy behaviour, or whether it had just swept it under the rug for calculational convenience purposes. So there wasn't much agreement about the physical interpretation, partially due to these sort of concerns about the mathematical standing of the renormalization procedure. So that's one problem. Another issue that became evident in the 1950s was that even after this renormalization procedure had been carried out and finite values had been assigned to each term in the series, actually Dyson argues that the series as a whole still wasn't going to converge. So there was a problem with understanding the sum of the series, basically. And this seemed to suggest that perturbation theory, this sort of approximation scheme which Heisenberg and Pauli had introduced, it wasn't going to be able to allow us to construct exact solutions of quantum field theories, and so it kind of didn't have the resources to answer the questions about the consistency of quantum field theory. Because even if we can construct series, that doesn't tell us whether solutions exist or not. Okay, so I'm thinking about axiomatic QFT and causal perturbation theory, these two programs I was talking about, as sort of each responding, like using those two sorry, this diagram might not be that legible. But I've got axiomatic field theory at the top, and here I'm saying that the large order divergences were in some sense the main problem that axiomatic field theory was responding to. So this issue with the sum of perturbation theory being ill-defined, and then causal perturbation theory is responding to the issue of how to understand ultraviolet divergences that occur at each term in the series, essentially. Okay, so just a little bit on axiomatic quantum field theory. Oops. Oh yeah, sorry, I skipped a slide there. So the way I'm thinking about it is that the main logic motivating axiomatic field theory is, okay, perturbation theory diverges, so it doesn't tell us anything really about the existence of exact solutions or not, so it's irrelevant basically. We need to reformulate quantum field theory in a way that makes no reference to this perturbative expansion, so it doesn't use the series expansion at all. And so the basic idea was to sort of, we need to specify what our basic objects are, and people had different ideas about that, and then write down sort of general conditions that they should satisfy. And this is why the term axiomatic comes in, because some people, there was some disagreement about whether to use this term axiomatic or not, but so someone like Whiteman was very enthusiastic about axioms, whereas Haag, so he was another sort of theorist in this tradition, doesn't tend to. Actually, Haag does use the term axiom. Some people wanted to talk about general quantum field theory or something rather than axiomatic. But yeah, so just to give some characterization of the different sort of ideas people were working with here. So in Whiteman's approach, the basic objects are operator value distributions, so that's the way that he characterized the field operators, and then the idea is you give some specification of those, and then we write down some physical conditions that they have to satisfy, like point array covariance and this causality condition. So that's basically just saying that these operators have to commute at space-like separated distances. So that's the sort of basic approach, and this tradition definitely had some important successes. So it allowed for more rigorous proofs of general structural results about quantum field theory, like the spin statistics theorem and the CBT theorem, and it gave a characterization of some of the general properties of quantum systems with infinitely many degrees of freedom. This issue of inequivalent Hilbert space representations, for instance, was sort of clarified by this program. But the main problem really was trying to connect these results to the empirically successful results of like mainstream theoretical physics. And one way to phrase this problem is basically we still don't know whether models of these systems of axioms exist in 4 dimensions, interacting models. So we don't actually know still today whether the standard model of particle physics can be understood as a model of these systems of axioms. So yeah, there was an issue with like connecting these results to empirically successful physics. Okay, so that's the sort of axiomatic field theory program. This second program I wanted to talk about, as I said, it's not as well known in the philosophy literature, took a very different approach to this sort of, I guess, the broad overriding aim of let's make quantum field theory more rigorous. Rather than getting rid of perturbation theory entirely, this approach basically can be understood as an examination of the mathematical structure of the perturbation series. So focusing on making perturbation theory more rigorous. So these physicists, Strikelberg and Boglebov, they were sort of the founders of this approach in the early 1950s, and they developed a different derivation of the perturbative expansion from the one that had been used by the developers of renormalized perturbation theory. So the reason it's called causal perturbation theory is that they derive the perturbative expansion from a causality condition. So they write down this general condition on the S matrix, and then they use that to construct each term in the series iteratively. Whereas Dyson had integrated a differential equation. So it's a slightly different, I'm not really going to go into that in detail, but they had a different way of deriving the perturbative expansion. And within that context, they developed a more sophisticated analysis of the ultraviolet divergences that occur in perturbation theory using distribution theory. So they were bringing in kind of relatively new ideas from pure mathematics, basically, which had just been developed in pure mathematics in around like 1950 as well. This approach led to a different diagnosis of the ultraviolet divergences. So I said in the 1930s people tended to understand them as a physical problem, basically, as like indicating that the theory breaks down at very high energies because you've got these infinities. In causal perturbation theory, they developed a different view of the ultraviolet divergences as essentially arising from the fact that you're multiplying together singular distributions in the perturbative expansion, in each term in the perturbative expansion in quantum field theory. So distributions are sort of, the notion of a distribution is a generalization of the standard notion of a function to include more singular objects like the Dirac delta function, for instance. One of the main ideas of distribution theory is to generalize the operations we can do on ordinary functions to this larger space of distributions. And you can generalize many of the important operations to distributions, but one operation that doesn't straightforwardly generalize is actually multiplication. We can always multiply two integral functions together, but we can't always multiply. The multiplication of two singular distributions is not always well defined. So Dirac delta times Dirac delta is not actually a well-formed product. The people working on causal perturbation theory pointed out that within perturbative quantum field theory, you're actually multiplying together singular distributions, and this is why you get these infinities. And they developed a treatment of these products that appear in perturbative quantum field theory. So one of the key results in the end was that we can actually provide a definition for these products of distributions. One way to think about this is to start with a restricted space of test functions which vanish at the origin, so that allows these products to be defined initially, and then the problem of renormalization in this reconstruction is a problem of extending these products to the full space of test functions. And this idea was set up by these earlier authors, Strikelberg and Peterman, and sort of developed later in the 1970s by mathematical physicists. So that's the basic ideas of this causal perturbation theory approach. the key result that comes out of this program is, well, they gave a sort of more rigorous reconstruction of renormalized perturbation theory, using these ideas from distribution theory. And I think that it does clarify, this program does have a philosophical upshot in that it clarifies the interpretive significance of the ultraviolet divergences. In particular, it shows that it's not really a physical problem. So that's still something that's slightly unclear in the physics literature. But I think this program does clarify that the appearance of ultraviolet divergences in perturbation theory, it doesn't actually indicate that quantum field theory breaks down at high energies. So it does have a kind of a philosophical upshot. However, there's still like a major limitation here because causal perturbation theory didn't address the large order behavior of the series. So it didn't do anything to improve the situation with the sum of the series. So we still, what you get out of causal perturbation theory basically is a formal power series. So you have a more rigorous way of constructing this formal power series, but you don't.
Do you mind asking a question?
Yeah, sure.
So how does it deal with the Landau pole with QED?
Well, I mean,
That doesn't exist.
so the Landau pole, I think of it as a non-perturbative problem ultimately. So the Landau pole doesn't. It doesn't pose a problem for the construction of the perturbative expansion. If you wanted to like try and construct an exact model by, starting with a cutoff structure and taking the limit of the cutoff, then you have an issue with the non-convergence. But so it doesn't address the Landau pole problem at all, essentially. So that's kind of what I wanted to talk about in the reflections. Really, is like that. This essentially just takes one problem, the ultraviolet divergences problem, and clarifies that, but leaves the other problems completely unresolved. I'm kind of coming up on time, so I'd better get to the
We started a bit late.
Yeah, okay. I guess I can take like 10 minutes maybe. So I wanted to conclude by coming to the theme of the workshop and talking about rigour in physics a bit, and I don't have very well worked out ideas here really. This is very sort of preliminary, and I wanted to get everyone's views on it. I guess like the problem I want to think about is how should we think about the fact that you have this overriding aim of making quantum field theory more rigorous, but you have these programs that are very, very different basically. They move in very different directions. They use different kinds of mathematics and so on. I think the key difference is the attitude which these theorists took towards the perturbative expansion. So this is a quote from Whiteman. So I'm not going to read that out actually, but basically what he's saying here is in the 1950s it looked like perturbation theory was not going to converge. So the problem is, can we develop some non-perturbative approach to quantum field theory? So essentially, perturbation theory is not going to solve our problems. We need to develop something new really. So axiomatic field theory was more ambitious really in its goals. It tried to move away from everything that had been done before, which had been based on the perturbative expansion, and develop a sort of completely new language for quantum field theory. Whereas this quote from Bogolubov, he's basically saying perturbation theory is all we have, or is like the only thing that's been successful so far. So it made sense to start there essentially. So causal perturbation theory was a more sort of conservative project in that sense of sort of starting with the frameworks that had been developed by physicists and trying to like incrementally improve their clarify problems of mathematical implarity that exist in those frameworks. So I wanted to sort of conclude by suggesting we could think of axiomatic field theory and causal perturbation theory as being motivated by different notions of mathematical rigour or different conceptions of how physics should be made rigorous. And I'm calling these sort of a global conception versus a local conception. As I said, this is very. I'm not convinced by all of this language, but here we go. So my one idea here is that, which is made very explicit by someone like Whiteman. So this paper by Whiteman in 1975, it's a retrospective paper on Hilbert's sixth problem. So Hilbert has these lists of mathematical problems, and the sixth one is essentially axiomatizing physics. And Whiteman basically says, this is what we were trying to do. We were doing Hilbert's program for quantum field theory. So the style of making physics rigorous here is based on this approach of sort of starting with well-defined objects and only using well-defined mathematical operations to build up from there. So rigour is sort of guaranteed essentially by the way that you're by your starting point and the fact that you're only using rigorous operations from there. So the focus of this sort of program is on the overall structure of the theory, which is why I'm using the term global, and establishing the consistency of the theory. And it kind of seems like using this approach, if you succeed, if you can recover the key results of an area of physics, starting with this axiomatic sort of program, then you've sort of solved all of the problems at once, essentially. Like all of the problems with mathematical clarity that exist in the physics literature have been sort of done away with. By contrast, I'm thinking of the causal perturbation theory approach as adopting a more local approach to the mathematical rigour, improving the mathematical rigour of an area of physics. So rather than kind of going back, sort of starting afresh and building up from there, the idea here would be that we can start from the physical theories as they've been formulated in the existing literature and try to resolve mathematical problems in a piecemeal way. So take a problem of mathematical clarity on its own and try and resolve that individually. And the idea here, the one idea would be that when we're doing mathematical physics in this more local way, we can sort of bracket some mathematical problems in order to clarify one. So in the case of causal perturbation theory, we can bracket questions about the sum of the series, and we can bracket questions about the existence of exact solutions, which then you will run into the Landau-Cole problem, and just say, can we give a more rigorous construction of each term in the expansion? And it looks like this approach is going to lead to a more kind of, the global approach is quite all or nothing in its approach to rigour, whereas this approach is more kind of allows for degrees of rigour and layers of rigour. I don't really know how to think about that exactly. So that's one of the problems that I'm leaving you with, I suppose, is kind of how to think about degrees of rigour. But yeah, just to give one last word before I finish. So I think like one of the takeaways here is just that not all projects in mathematical physics are axiomatic in their spirit, and philosophers, because philosophy of science has been very influenced by the axiomatic tradition, we I think people are being really attracted to axiomatic quantum field theory for that reason, and sort of haven't noticed these other approaches which are also going on in mathematical physics. So yeah, we may need to sort of broaden our view of what making an area of physics rigorous amounts to. And I'll finish there.
I'm Cherry, so I'll stand up.
So I guess we've got 50 minutes, right?
Okay, great.
Yeah.
Questions? Okay, got you guys in the list, so keep your hand up if you have any questions.
That was very interesting, thank you. So the main kind of question that was always there, especially with the contrast to axiomatic quantum field theory, is that causal perturbation theory seems to want to better distinguish math and physics, in contrast to axiomatic field theory that wants to kind of combine them. Because it seems that when you talked about the ultraviolet diversions and how causal perturbative theory solved it, it showed that it was just a mathematical artifact. It doesn't have a physical interpretation. So it seems to want to more separate, like the local approach that you're proposing seems to actually want to further separate math from physics. So with that we're able to tell what problem, when you face a problem, whether it's a mathematical problem or whether it's there's a physical counterpart and it's a physical problem. So it kind of goes the other way, where it's like physics is first. We take what we know from physics, we give it mathematical formulation, and then we check we check to see where the problem lies in math or physics.
As opposed to axiomatic.
As opposed to axiomatic, which is like, no, we start with math, and then we try to reach the physics. We try to find the middle ground, essentially.
Yeah, that's interesting. I didn't mention in the conclusion, I was intending to go back to that you might think this local approach to rigour is not very philosophical because these questions about sort of overall consistency are often viewed as being the kind of questions we should be focusing as quintessentially philosophical somehow. But I think that causal perturbation theory does, as I said at one point, does have interpretive consequences in the sense that, as you said, it clarifies this problem. It allows you to figure out whether this issue is a physical issue or a mathematical issue, and basically shows that it is a mathematical issue. And so I guess that's kind of a negative conclusion in a way, in that it's saying it clarifies what ultraviolet divergences don't imply. But I think that's still conceptual progress. I'm not. Maybe there's something to your. I'm not quite sure I have your intuition that there's a big difference regarding separating maths and physics.
So I have a very simple idea, right? With general relativity, the field equations, they're mathematically formulated, but they're not mathematical. There's no axiomatic way to get to them, right? The axioms are of non-Euclidean geometry, but then the field equation is just added as an additional constraints. Right? We always talk about the light cone, what you can, violating causality, but anything within the constraints of general relativity, that's fine. You have many contradicting models within general relativity, and that's fine. Then use experiments to find out. But the math and the physics are quite well delineated in that context, and the physics just becomes a constraint, essentially. The field equation. The field equation become constraints, essentially.
Additional constraints.
Additional constraints on the non-Euclidean, let's say, definitional axioms. It just becomes another axiom-like function without specifying objects or anything of the sort, right? Anything that has mass is going to be affected. It doesn't matter what it is. So you can create universes that are purely radiation, universes that are purely matter, and you can contrast them, and that's all fine. Sorry, I'm going to...
I think we probably need to maybe come back to this in a more open discussion we can have at lunch or later. You're next.
Yeah, thank you, James. I got two questions, but maybe I'm just going to ask the first one. later. I'll ask the second. The first question is, well, the question is, so if there is a global and a local aspect of rigor, and the one being like championed by QFT, the other by causal perturbation theory, and you say that global implies that basically if the program is successful, it solves everything all at once. How then to think of, because you presented it as two approaches to solving different problems. I know that people in AQFT, like Asia Resner, has developed kind of a meeting of the two, a bridge between the two, like perturbative AQFT, mainly because she wants to solve the two problems. But then it's like, do you think of them, like, does this distinction still hold between a global account of rigor and a local account of rigor, or are they just two approaches solving different problems?
Yeah. Thank you. As you know, I wrote a paper with Kasia recently. I think when I first formulated, because this is based on like something that I wrote a few years ago and abandoned, and at the time I didn't know about perturbative AQFT. So this is an approach that's like essentially bringing these two strands together and using the construction you get from causal perturbation theory of this formal power series and translating it into like algebraic language. So
that's
you
really
can set them.
So you could have your lines going back again.
Yeah, in the paper with Kasia, I had the lines going. I had another diagram. So this continued. This diagram, you can't see it, but I had like those two lining up again with perturbative AQFT.
That's great.
I don't really know how to think about it in terms of like this idea that they're motivated by different notions of rigor. I think I should have thought about that more. I mean, I guess you can still have two programs which are motivated by different aims, or you use different methodological strategies, but ultimately end up converging. That doesn't mean that there's no difference, if you see what I mean. So maybe that's one way that you could. I don't know whether you were using this as a This could be a challenge to the idea that these programs are really that different in the way that they're employing notions of rigor. But
it was not so much a challenge as a question as like on what you said on the global account of rigor, because if it's global, then it doesn't need the local, like the addition of the local rigor from causal perturbative theory. If it's another response to another problem using another local account of rigor, then it might make sense. But I'm not sure that.
I think you should say that the perturbative AQFT is just a bigger local approach rather than a global approach. No?
But they are trying to. So essentially, what happens is they use the tools developed in causal perturbation theory to construct models of AQFT.
Okay.
Yeah.
So maybe
but they have to like slightly generalize the Hug-Kastler axioms to allow. Basically, you have algebras of formal power series. So yeah, you have to like.
So it's like a way of it's a way of combining them.
Yeah.
That's very interesting. Did you want to follow up with more? Or are you guys happy with this? Alex?
Thanks, I really enjoyed this. Well, I had a trivial question, which is wondering whether the word, like the application of the word is causal here, but that's boring, so you can answer that later.
I've got a paper about that.
Okay. Maybe it's not boring.
So I've got a paper with Alexander Bloom called Perturbative Causality. So that's on like the more historical side, but we're specifically talking about the causality conditions and what they have to do with causation a bit.
Okay.
Not very well, but there's a bit of philosophy in there.
So the more substantive question is how to relate this to effective field theory approaches. So the thought being that local rigour is something that we might want to achieve insofar as it kind of like cleans up and sets on firmer footings the kind of a theory that's within a given domain and applicable within a domain. And global rigour is not the kind of thing that we should be aiming for, because we know that our theory doesn't apply absolutely generally. We know that there are limitations to its applicability. And so the idea of starting axiomatically in the way that people standardly do in AQFT might be mistaken or misdirected. And so not that, you know, they're both things that we might want to achieve, and local sort of sets us on the path to global, but the global is going down the wrong track. Is that a way that you think works, or the right way of thinking about what's going on here?
You certainly could run that line, I think, and that could be one way of cashing out sort of Wallace's worries about axiomatic field theory.
This is a Wallacean.
Yeah, well, so Wallace focuses on the fact that the current axiomatic formulations of quantum field theory do include the assumption that there's infinitely many degrees of freedom in any finite volume, and he thinks that's not an assumption that is physically motivated. So the way that he phrases it is more, at least as I recall, it's more as a critique of the specific axioms as they're adopted. But the way that you're developing the idea would be the axiomatic sort of methodology is just is not the right one. So it's not like, oh, if we fiddle with the axioms a bit, then we'll be all right.
You know the physics better than me, but as I understand it, the way it's often set up is that we can get something like effective renormalizability if we kind of deal with our perturbation series order by order and then stop at some point. And that looks like appropriate to the causal perturbation theory type approach. And that is sort of, and the justification is a little bit hand-wavy, but that's kind of heuristically warranted by thinking like our physics applies to a certain scale and then beyond that it won't apply. And then the global approach, the AQFT approach, says we should, try and do it all orders all at once, which seems to have some kind of connection to thinking we should go down infinitely deep. And if we think that the going down infinitely deep is just a misapplication of a domain-limited physics, then we might well think that global rigour is not the kind of thing we should be aiming for.
I do think, just one quick comment on that though, I do think there are good motivations for going beyond perturbation theory and trying to develop non-perturbative physics. And historically, I think in the 50s people were quite optimistic about that. They thought perturbation theory has basically outlived its usefulness, we need to develop non-perturbative physics. And I think that was a big part of axiomatic field theory at the beginning, was like an optimistic view of like what you could do without using perturbation theory. And I think that motivation is good, and potentially isn't tied to those sort of more dubious ideas. But yeah, it ended up not panning out.
Yeah, go ahead. We were going to go until...
should we
till
have like 5 to?
Okay, we're going to one more question then.
Yeah.
Go ahead.
So my first one was more a remark, is you talked about utilization of QFT, but it reminded me of the fact that there are also debates about the rigour within what you call the conventional QFT. So for instance, I was thinking about the debate between Feynman and Schwinger in the 50s, so that's the time frame we were considering, about where to start in the field. What should be the dynamical axioms or postulates, say, to start? So of course Feynman was arguing for the path integral, but Schwinger thought that this was not a good idea because the path integral is not doing well. defined. So he argued that no, we should start from a differential variation principle, which is called the quantum vacuum principle. And but obviously the two are relative. They are equivalent, but they are not on the same level of rigor. So I was wondering if you also thought about the limits of rigor within this.
Yeah, because Schwinger actually uses the term rigor, from what I recall.
He was.
Yeah, that's. I think also Alexander Bloom has been writing this book about debates about the inconsistency of QFT in this period. I'm not sure if he uses it in the book, this term in the book, or just in conversation with me, but he uses the term like middle brow. So there's like mathematical physics stuff, there's like very unrigorous physics, and then there's like the middle brow stuff that is still like trying to address these more foundational questions and using some notion of rigor often, but isn't, going the full hog, the full like way to.
I mean, it's literally what I will talk about. So hopefully, I didn't know I was doing middle brow philosophy physics. I do now.
But that's another way to, I guess, raise this question that I mentioned at the end of like, how should we think about degrees of rigor? It's, I don't think I really have a good answer there, but I think it's like a really interesting question for how we should really think about all of these different projects that are using a notion of rigor, but in different ways.
Should we thank James again?